Want to continue? Hello, Math 271 students. In this video, we're going to take a look at the question, what is a derivative? There are two different points of view we can take with derivatives. Here's our first working definition. The derivative is a formula which allows us to calculate the instantaneous rate of change of a function at any point. The second point of view is this. The derivative is a formula which allows us to calculate the slope of the tangent line to the graph of a function at any point on the graph. Both of these points of view are equally correct, and it turns out that they both describe the same thing. Now, before we get into any examples, let's talk just a little bit about notation. It turns out that there are four kinds of notation for the derivative that you might commonly run into. The first is called prime notation. So if our function is something like f of x equals some stuff, then the derivative of f of x would be denoted f prime of x. So notice that the little apostrophe looking symbol is read prime. So f prime of x means the derivative of the function f of x. If we have a formula written as y equals something like, say, y equals 2x plus 7, we can also write that as y prime. So y prime, notice we put the prime on the name of the dependent variable. So f prime of x or y prime. Now, one of the two inventors of calculus was a man named Leibniz, and his notation is still very widely used, and it is probably the most useful version of the notation for the derivative. The way Leibniz wrote derivatives is he would say dy dx. What this means is the derivative of y with respect to x. So he's telling you, he's taking the derivative, that the range variable is y, and that the domain variable is x. You can also use this as an operator. So you can say d over dx like so, and then you can actually write a formula in here. So what this means is take the derivative with respect to x of the function defined as 2x plus 7. Or we can use function notation, d by dx of f of x. So Leibniz's notation is extremely useful because it can be used in lots of different ways. The third kind of notation is operator notation. We use a large capital D to say we're going to take the derivative, with a subscript that is our independent variable. So in this case, the derivative with respect to the variable x, and then after the d sub x, we put whatever we're going to take the derivative of. So we could write the name of a function, f of x, or we could put in a formula, something like our old 2x plus 7. The fourth kind of notation is Newton's notation, Newton being the other person who discovered calculus at the same time that Leibniz did. Newton's notation is not used very often anymore, mostly because later on down the road it becomes fairly clunky and isn't very friendly to use. But here's how Newton indicated the derivative. If he was writing the derivative using the output variable, then he would indicate the derivative by putting a dot over top of the name of the variable. Or if he was writing the name of the function itself, f of x, if we were using Newton's notation, again we would put a little dot over top of the name of the function. So that's Newton's notation for the derivative. So we have prime notation, Leibniz's notation, operator notation, and Newton's notation. Prime notation and Leibniz's notation are used the most often, and those are the two you'll see most of the time in this class. Operator notation is fairly new, but it is used more and more, and you're most likely to see that when you first get to probably differential equations and maybe calculus 3. And Newton's notation is one of the earliest notations, but you don't see it used very often anymore because it's not as user-friendly as the other notations. So now let's actually talk about what the derivative is. So first, let's consider the derivative as the instantaneous rate of change of a function. Let's start out by thinking about linear functions. So linear functions pretty easy to graph. Let's say here's a coordinate plane, and I'm going to put a linear function on here, and maybe it's a constant function. And let's say that's the constant function y is equal to 3. So if I look at the rate of change of a function, I can talk about the average rate of change. I can pick a couple of points that live on this curve and fill in their values. So maybe that's 2, 3, and 6, 3. And I can calculate the average rate of change of that function between those 2 points. So to calculate the average rate of change, we find the difference in the y values, divide that by the difference in the x values, and what do you know? We get 0. This ought to make sense because this is a constant function. It never changes, so its average rate of change is 0. Now, if I look at one particular moment in time and ask, how is the function changing at this one specific spot? Well, because it's a constant function, the instantaneous rate of change must also be 0. So I can look at this and say that y prime is equal to 0. So this is fairly simple when we've got ourselves a nice constant function. But let's suppose that the function is not a constant function. So here I have another linear function, but this time it's not constant. It's y equals x plus 2. I can still think about the average rate of change of this function the same way I did before. I can pick 2 points that live on my function. So let's say we pick -2, 0, and we go over here, and let's say we pick 1, 3. I can calculate the average rate of change for this function. 3 minus 0 divided by 1 plus 2 is equal to 1. So the average rate of change of this function between those 2 ordered pairs is equal to 1. And it actually doesn't depend on which ordered pairs I pick. I can pick any 2, and I'm always guaranteed to get an average rate of change of 1. And that's because this is a line. The thing that makes a line is that its rate of change is a constant. So it doesn't matter whether I have a constant line, y equals 3, or if I have a line that is not a constant function, y equals x plus 2. The average rate of change, or the rate of change of that function, is its slope. So that means that for a linear function, because it is a function with a constant rate of change, its derivative has to be the value of the slope. So y prime equals 1 here. Now let's think about what happens if our function is non-linear. Let's suppose that we look at something like, say, a parabola. Y equals x squared is a nice simple non-linear function. The thing that makes a non-linear function a function is that the rate of change is no longer constant. So it depends on where I look on this function as to how rapidly it is changing. So that's where that idea of tangent lines is going to come in. Now, I'm going to build this up in little stages. Let's start out with the average rate of change. If I pick 2 points on that curve, I can draw a line in between those 2 points that's called a secant line. So that red line is a secant line. And the average rate of change is the slope of that secant line. So let's suppose this first point over here is -1, 1. And the second point is 2, 4. So the average rate of change between those 2 points is 4 subtract 1 divided by 2 plus 1. And I say, well, okay, that's 3 over 3. The average rate of change between those 2 points is 1. But let's suppose I switch secant lines. So now, instead of starting at negative 1, 1, I'm going to start at 0, 0, and I'm going to recompute the average rate of change. Well, if I do that, then I'm looking at the slope of a different secant line. So now my average rate of change is 4 minus 0 over 2 minus 0, which is equal to 2. So what we come out with is the average rate of change for this function depends on where we start and where we stop on our secant line. Now let's zoom in a little bit on our picture. So this is still y equals x squared, but now I'm only interested in a little sliver of this thing in the first quadrant. One thing that it would be handy for you to do is pull out your graphing calculator and graph y equals x squared and start zooming in on that quadrant 1. So let your x minimum always be 0, and for your x maximum, start decreasing the value of that x max. Get it closer and closer and closer to 0. So start with something like 5 and keep decreasing it until you get down to 1 or 1/2 or 1/4. And take a look at what happens to that picture. And what you should notice is that the curviness of the picture starts to go away. The closer you zoom in, the more the curve is going to look like a line. And that's actually an important idea. So take a minute, pause the video, do that in your graphing calculator, and then start back up again. Okay, so hopefully you've got this idea that if we zoom in close enough, that curve looks a lot like a line. Now, let's go in here and take another look at these secant lines. So now I've drawn a secant line in between 0, 0, and 2, 4. So I can calculate my average rate of change very quickly. It's 4 divided by 2, or 2. Now, I'm going to start moving one of those coordinate pairs closer and closer to the other one. So now I'm going to take 0, 0, and I'm going to move it up here to 1, 1. And I'll redraw my secant line. Notice my secant line is a lot closer to my curve now. And if I recompute the average rate of change, I end up with 3 instead of with 2. So it's larger than it used to be. And now I'm going to move that up just a little bit more. I'm going to slide that 1, 1 up a little closer to 2, 4. So here's my point. And notice that now I'm really having a hard time seeing the difference between my secant line and my curve. If I keep zooming in and zooming in and zooming in, let's say there's the little piece of my curve. There's my 2, 4. Eventually, I can have those things sitting practically on top of each other. And my secant line, when they eventually do sit on top of each other, grazes that curve at that one point, and instead of being a secant line, is now a tangent line. So I've gone from average rate of change is the slope of a secant line to the instantaneous rate of change is the slope of the tangent line. So that's where we get that idea that the instantaneous rate of change and the slope of the tangent line are the same thing. And that's why we need limits. This process of sliding these two ordered pairs that are the endpoints of our secant line closer and closer together until there's no distance in between them is a limiting process. So we have this question, what is the connection between derivatives and limits? It turns out the derivative is a limit. The derivative is the limit of the formula we use to compute the average rate of change of a function. And if you think back to your pre-calculus class, we had a fancy name for that average rate of change of a function. It was called the difference quotient. And it had a really fancy formula. It looked like f of x plus h minus f of x divided by h. But really, that's just a formula for the slope, where f of x and f of x plus h are the y-coordinates of our two ordered pairs, and h is the difference in the x-coordinates. So if we take the limit of this difference quotient as h goes to 0, in other words, as we slide those two ordered pairs closer and closer and closer together so that the distance between them approaches nothing, then what pops out the other side is the derivative of our function. So that's the connection between the derivative and limits. The derivative is the limit of that special function called the difference quotient. So now that we've addressed limits, what about continuity? What's the relationship between continuity and differentiability? It turns out that there are two different ways to look at that relationship, and I've got them both posted up here on the screen. The first theorem, or the first version of the theorem, says if a function is differentiable at a value n, then the function is continuous at that value n. So this means that if we can take the derivative and show that that derivative exists at a particular number, then we automatically know that our function is continuous there. The other way we can state the same theorem is we can say that if a function is not continuous at a value n, then the function is not differentiable at that value n. So in this case, we're starting with the idea of continuity, and we're saying, well, if we already know there's a spot in this function where there's a discontinuity, then that tells us that it doesn't do us any good to try to take a derivative at that spot because it's not going to exist. So if we start with differentiable, we say if the function is differentiable at a particular number, then we automatically know the function's continuous at that same number. If we start with continuity, we can say if we already know our function is not continuous at a particular number, then we also know the function won't be differentiable at that same spot. So let's take a look at a couple of examples, and these ought to look familiar because these are a couple of functions that we looked at in our video on limits and continuity. So in this function, I'd really like to know where I can take derivatives and where I can't take derivatives. So the first thing I'm going to do is see if I can find the discontinuities, because I know that if there's a discontinuity, then I won't be able to find the derivative. So I see that at 1, my function's not defined, so I won't have a derivative at 1 because my function isn't continuous there. I also see that I have a problem at 2. The function is defined and the limit exists, but the limit value and the function value aren't the same. So I'm not going to be able to find the derivative of this function at 2. I go over here and look at 3. Again, no derivative there because I have a discontinuity. The function is defined, but unfortunately the limit does not exist at 3. So at 1, 2, and 3, we know in advance that this function does not have a derivative at those values. Now, just because we know the function is continuous does not mean we necessarily have a derivative. So it's a little trickier going forward. And to see what I mean by that, let's take a look at our second example. So here's our second example, and we can very quickly see where, yeah, there's not going to be a derivative. There's no derivative right here at 2, because our limit fails to exist. No derivative right here at 3, because the function's not defined there. And we can see that there's no derivative right here at 4, because the limit value and the function value disagree with each other. So 2, 3, and 4 are locations of discontinuities, and our theorem says not continuous means not differentiable. However, continuity does not, I repeat, does not guarantee differentiability. And this function has a big illustration of why. There's one other place where we can't take a derivative for this function, and that's right here at 1. Remember that our definition of the derivative says that the derivative is the slope of the tangent line to the function at that point. Now, Notice that on either side of 1 we've got nice lines, and 1 is the place where we change which line we're on. So remember, this is a piecewise defined function. Now lines are their own tangent lines, so up until I get to 1, I'm going along like this. And I can very quickly calculate the slope of that little red piece right there. I see that I'm starting out at 0, 1, and I'm ending up at 1, 3, and so I can calculate the rate of change as being 2. But once I get to 1, I do a switch over. Now I'm going along on this line, right here. And I can calculate the slope of that line. I see that I'm going from 1, 3 to 2, 2. So I can calculate the slope of that little line segment. I say, well, that's going to be negative 1. So right here, where I switch over, the question is, well, which one of those things is really the tangent line? Is it the first line or the second line? And the answer is it's neither. There is no good tangent line right there because the amount of change is so abrupt, we can't talk about the instantaneous rate of change at that particular point. That particular point has a special name. It's called a sharp point. You might also see a sharp point called a corner. So a sharp point or a corner is a spot on the graph where the rate of change changes so abruptly that we cannot calculate a derivative for the function at that spot. So when is a function not differentiable? A function is not differentiable anywhere where it is undefined. A function is not differentiable at any sharp points or corners on the graph. And then there's a third spot where our function will not be differentiable, and that is anywhere where the tangent line to the curve is a vertical line. So let's take a look at another example where we'll have a vertical tangent line. So here's a function that has a vertical tangent line at one spot. Y equals the cube root of x. And I would highly recommend that you take this function and draw it in your graphing calculator so you can get a really good picture to work with. Notice most places I'm not going to have any trouble drawing tangent lines to this curve. So right there, and no trouble drawing a tangent line. I'm going to have a hard time telling the difference between it and the curve itself, because this cube root function, it changes pretty slowly in most places. It's fairly flat. Same deal over here. I can draw tangent lines wherever I like. Where I'm going to run into a problem is right here. When I'm over here in the center of the coordinate plane, this function goes from curving upwards to curving downwards, and it does it extremely abruptly. And it turns out that right here in the middle, the function is so steep that the tangent line to the function is vertical. So that's the one spot where I can't take the derivative of that particular function. And I would encourage you to take your calculator and zoom in around the origin when you have a graph of y equals the cube root of x, and notice just how steep the graph is right there. Convince yourself that, yeah, the tangent line at that particular spot really is a vertical tangent line. And then we'll be able later on in the session to see just exactly what that tangent line looks like. So here's a last little example for this set. Here we have a function y equals g of x, and your job is to take a look at this graph and find all the values in between 0 and 4 where this function does not have a derivative. So pause the video, write down where this function is not differentiable, and then restart the video to check your answers. Okay, so let's see how you did. So remember, there are 3 places where our function isn't going to be differentiable. It won't be differentiable anywhere it's not defined. It won't be differentiable at any sharp points, and it won't be differentiable at any spots where the tangent line is vertical. And we can see we meet 2 of these criteria in this picture. So right here we have a spot where the function is not defined. So when x equals 1, this function will not have a derivative because it's not defined there. And we can also see that this function has a sharp point at x equals 2. So because there's a sharp point at x equals 2, this function will not have a derivative at x equals 2. This picture, we don't have any vertical tangent lines, so we don't have to worry about that one. And there we have it. Now you have a basic idea of what a derivative is and where derivatives exist.